Okay, welcome everyone to the dynamics lecture. Just figure out what I'm supposed to do here. And let's push start video. That sounds like a good idea. Hey, I've already got a student. Taylor's on board.
Hey, how's it going?
Yeah, doing great. It rained on me a little bit this morning.
I'm sorry to hear that. It's still raining out here in Owasso a little bit.
That's good.
hmm The flowers are liking it.
Uh, Now I'm wondering if I need to adjust this to where you can read all that. Looks like you can read that pretty good.
Yeah, I can read it.
Okay. Let's see if anybody else showed up here, Taylor. Nope, it's just you and me. It's nice to get to know my students. How old are you, Taylor?
I'm 31.
Oh, you're an older guy.
I'm an older guy.
Yeah.
Uh, I was doing sales for about 6 or 7 years. I went to OSU when I was 18 and then dropped out when I was about 19. And I did sales for a couple of years and decided I wanted to get into something else. So I came back to school about 3 or 4 years ago, and I'm still working on that engineering degree.
Well, here's my theory on that. Right now you're 31. It's going to take you probably about 3 years to get that, maybe four, I don't know, depending. But see, in 3 or 4 years, you're going to be 3 or 4 years older. Whether you got the engineering degree or not, you're still going to be 3 or 4 years older.
That's right. That's right.
If you might as well be 3 or 4 years older with the engineering degree.
And I really do enjoy learning a lot more now than I did back then.
Well, this is fascinating stuff. I love this stuff.
I think so too.
And yeah, it's good to love what you're doing. This is today. It's about pulleys and how they work,
Okay.
and it also applies to gears and pulleys. Well, okay, good. We still have 7 minutes before class, and you're my only student. This is a one-on-one right now. Do you have any questions on anything?
Um, Nothing comes to mind right away. Do you mind if I go grab my notes real quick?
You take your time, do whatever you want, fix your coffee.
Just took notes over 12.8 last night, and I don't really have too many questions over that right now.
12,
About where are we at with the lecture? What chapter? What part of the chapter?
it's the tail end of chapter 12, I think, with the pulleys.
Do you know what
We gotta
section
learn
that
how to
is?
work, gotta learn how to work these pulleys.
Okay.
Have you tried watching the YouTube video?
I haven't yet. I watched one last week.
Nice to have it there
Mhm.
in case you miss or in case you don't understand. You could watch it over. That might help.
It does sometimes.
Did you go to OSU Stillwater or OSU Tulsa?
OSU Stillwater.
Yeah.
I was there last year actually, and I was bartending over at Murphy's down on the strip, but then COVID came along and closed everything down. So I decided to move back home and save some money while I'm finishing
Good
up.
for you, Taylor.
Thanks.
Well, I've never done any bartending. I'm a Southern Baptist, and we're not supposed to drink at all.
Well, you're not missing out on much. Their drinks were pretty good.
Ah. Well, I guess it's about, it's almost that time. Let's see if we got any more customers here. Oh yeah, look at this. We got Braxton, Ashley, Taylor, and Nicholas so far. We're doing great. Guys, class starts in 2 minutes. Here's your chance to ask me something. You have any of you have a comment or question?
Not me.
Not me. Okay, well, I guess we could get started. The first topic is dependent motion. That's when two bodies, their motion depends on one another. Like for instance, a pulley. They have a lot of different kind of pulley setups in this chapter. We'll just look at this one here. I happen to be on page 85. And they have a pulley set up like this. But you can tell if this is B and this is A, you can tell that if pulley B goes down, A will go to the left. If this mass B goes up, A will go to the right. Now my guess is B is going to go down, and A is going to go to the left. I don't think B is going to go up unless somebody pulled on A, and I don't see any forces there on A. So the interesting thing is they're dependent on one another, but you'll discover that A goes twice as fast as B. If B goes down maybe 2 inches, A will scoot over to the left 4 inches. It will go twice as far. The equation is called the dependent motion equation, and it would go like this. That's the dependent motion equation. It's the dependent motion equation. You're looking at it. Now I need to explain to you guys how I got that and how you can get it. And then we'll talk about relative motion here in a little bit. But like, for instance, if B has a velocity going down of, oh, I don't know, let's say 2 meters a second. Well, if you do the algebra, then you'll discover that the velocity of A would be -4 meters a second. I mean, the algebra says 2 times 2 plus a -4 equals 0. Well, guess what? A goes to the left, and it goes to the left twice as fast. Twice as fast. That's the dependent motion equation, and I need to show you how to get that. There's several ways. Now, when they wrote this, they wrote it like this on page 86. They wrote the dependent motion equation like this. They put a minus here. No. I need glasses, my wife tells me. That's an equal sign. But that's the same thing that we did, pretty much. Well, no, not exactly. Not exactly. Because, see, 2B is not equal to VA. It's equal to a negative VA, right? So they're kind of confusing us. What they did was they decided going to the left was positive for A. And so if B was, they said B going down is positive and A going to the left is positive. So it's a matter of how you define your positive and negative directions. Well, I don't know if that made any sense, but let's do some here. Let's do this one here maybe. That's too hard. Let's do an easier one. Why don't I do an easier one? They had to go and make things complicated there. Let's just put A right here. And we need to write the dependent motion equation for that system. Now, the way the book says to do this is you make a can't think of the word, but we're going to call this y of B a variable. You're going to make a distance variable And we're going to measure everything from up here where the pulleys are attached. And then we'll make this distance variable here for A, y of A. And here's the plan. We're going to add up the lengths of this rope. See this rope here? It's the movable rope. See, this here isn't moving any. In fact, this doesn't, you don't even need a rope here. You could use a strip of metal. And same here. You could have a rope, or you could just have a strip of metal. But the way the book says to get this dependent motion equation is you take this length of this rope here. Here, let me color it. I've got some red here. We're going to color this red piece of rope right here. Now that's equal to, that length is equal to y of b minus this length here. That's just a constant. Can we call it, give it a name? How about K1 would be good. You understand, if you take y of b and you subtract this K1, you get the length of that red rope. And we're going to add up the whole rope. Now we're going to go halfway around this pulley. Now, all the way around the circle is 2 pi r, so halfway around is just pi r, where r is the radius of your pulley. We're adding up the lengths of the rope. Now we're going to add up this length right here. See this length of this rope right here? That length. Does that come out in red? Kind of. Okay, now that length is y of b minus the K1 minus this length here. Why do we call this length here K2 might be? It's just some constant. K2, there we go. So if you subtract K1 and K2, here's K1, here's K2, and if you subtract those from y of b, you'll get this little piece of rope, won't you? Yeah, I think you do. Okay, now let's add the half of the circumference of this pulley here. Now it's not 2 pi r, it's just pi r. So we'll add that, plus pi r. And now we only have one little piece left. You see this piece of rope here, from here to here. And that will be y of a minus that K2. Now, did all that show up on? Yeah, that all showed up. I don't know if you can read my writing, but there you have it. Now, what is this all equal to? It's equal to the length of that rope. I don't know what to call it. How about L would be a good name? Just call it L. We've added up all the lengths of that rope. Now, the length of that rope is a constant. We're going to take the derivative of all these. When you take the derivative of this, you'll get V sub B. When you take the derivative of that constant, that K1 is this piece of metal or whatever, right, from here to here. That's just 0, just a constant. The derivative of pi r is a constant. The radius of that pulley doesn't change. Pi doesn't change, so the derivative is 0. The derivative of yb is the velocity of b. The derivative of that constant there is 0, minus another 0 for that constant, plus a 0 for the derivative of that pi r, plus the velocity of A, that's the derivative of YA, minus the derivative of a constant equals 0, because the derivative of the constant L, the length of the rope doesn't change. And now let's finish writing this. It looks to me like you got 2VB plus VA equals 0. We just figured out the dependent motion equation for that system. Do I need to go over that? Anybody need help with that, or are you okay? Because if you're okay, we're going to do some more.
Where did that second VB come from in the 2VB?
Well, you got a VB here and you got a VB there. That makes 2 VBs.
Gotcha. Okay.
Thank you for asking. Okay, we're going to do some more now. Go to well, before we do a different one, let me show you a much easier way to do this. There's a much easier way to do these. And the book doesn't tell you this. This is just between you and me, top secret, okay? Pick out the body that just has one rope on it, and it's got this rope here, and there's tension in that rope. Let's call it T, okay? Now these are what they call massless, frictionless pulleys. And when you wrap a rope around a massless, what they mean by massless is that maybe that pulley weighs about 10 grams, but these bodies here could be 1 or 2 kilograms. So essentially they don't affect the motion at all because they're so lightweight. But what I'm trying to tell you is you have the same tension in this rope, even though it goes around the pulley. And this goes around this pulley, and you have the same tension in this rope. And then what you do is you just count the tensions. Notice B has 2 tensions on it, so you write 2 VB. And A only has 1 tension on it, so you write 1 VA equals 0. Hey, that was a lot quicker and easier, wasn't it? That was a whole lot easier and quicker than going through all that mess about adding up the lengths of the ropes. Let's do another one so that you can feel secure about this. Any comments or questions before we do a different one?
Nope.
Okay, we'll say goodbye to that one there. How about this one? This is fundamental 1239. And it looks like we have a now, they don't have a mass here, but we could put a mass there. I'm just going to go ahead and put a mass there so we don't get too confused. Here's they decided to call this D for some reason. And This comes up here to another pulley. There we go. There. Now there's just one rope here. See this rope? It comes up here, it goes around here, goes around here, goes around there. There you go. There's just one rope. And you can use the same method that the book teaches. Let's do that. Now they said that A is going down 3 meters a second. We'll get to that in a minute. They say A is going down 3 meters a second. Now you can tell by looking at it that D is going to go up. If A goes down, D goes up. So their motions are dependent. But here's where you need these reference distances. Call this y of A. We'll call that y of A. And we'll call this, they never gave a name for this. We got A, B, C, D. Why don't we call this pulley E? That'd be a good name for it. I'm going to call this little guy here C. I'm going to call this distance here y of E. Now there's going to be some constants in here. I don't know, you could call that K1 maybe. And see this distance here, you could call that K2. And see this distance here, you could call that K3. They don't get longer or shorter, they're just fixed. Can you read all my writing? Maybe. Probably need to write bigger. This is K1. Okay, now using the method that the book teaches, we're just going to add up the length of this rope. See, this rope comes up here, goes around, comes up, goes around. We're going to add up the lengths of the rope. All right. Well, this first length, let me color that. We're going to add up this piece of the rope right here. There you go. See it? You know what that is? That's y of A minus K1. And then you got to go, the rope has to go around that pulley. So that would be halfway around. Instead of 2 pi r, that'd just be pi r. Now these pulleys have different radii, but we don't care. It's going to drop out anyway when we take derivatives. And then we need this length here of the rope from here to here. We're going to measure that. That's going to be y of E minus K1. And then we have to go around this pulley here, halfway around this pulley here. And that'll be, it's not 2 pi r, it's just pi r. It's a different r, but I don't know, if you want to call it R1 and R, we'll call it pi r prime or something. Those are going to drop out when we take derivatives. Hey, we got this little piece here now. We've got to go from here up to here. And that is y of E minus K2. Yeah, okay. Then we have to go around this little pulley here. I know the radius might be smaller, but we don't care. I'm running out of room here. I'll go down a second row here. I've got plus pi r, never mind, put a 3 on there if that makes you happy. And then finally, we got this piece of rope that goes from here to here. And that'll be y of e minus k2, right? Yeah, I think so. Plus y of e minus k2 equals the length of that red rope. Call it L maybe. And then you take derivatives with respect to time, and you'll get the velocity of A. That'll be a 0 when you take the derivative. It's a constant. That's a constant. Pi doesn't change, and the radius of the pulley doesn't change. But this gives you VE. And then that's a constant. The derivative is 0. Constant derivative is 0. Plus VE. And you take the derivative of y. Minus a constant. The derivative will give you 0 plus 0 plus VE minus 0 equals 0. The derivative of the length of the rope, which is a constant, is 0. So the bottom line is you have VA plus 3VE is equal to 0. Now, E and D are connected. Whatever the velocity is of E, it's the same velocity as D. So you could say VA plus 3VD is 0, because they're the same. You can see that. Whatever that pulley does, that body D does. So we finally, after long last, we finally have the dependent motion equation. There it is for problem F1239. Now let's answer their question. They want the velocity of D if the velocity of A is 3. Okay. Now they chose to say 3 is going down as positive. So if that's 3, my algebra tells me that the velocity of D is minus 1 meter per second, because 3 plus 3 times minus 1, the algebra does that. What does minus 1 mean? Well, that means that D is going up, not as fast. It's going up 1 meter a second. A is going down pretty fast, and B is going up slowly. And if you want to look at the answers in the back for F1239, let's see if we got that right. F1239 says here, it says here that the velocity of D is negative 1 meter per second, or you could just say it's 1 meter per second going up. So that's how the book teaches you to do it. Now let me show you my secret way of doing it for you. See this body here that's got one rope on it? We're going to put a tension on that rope. Going around this pulley, you got the same tension here. Going around this pulley, you got the same tension here. Going around this pulley here, you got the same tension here. Now we're going to look at this body D here. It's got 3 tensions pulling up on it. So the equation is going to have 3 times the velocity of D, because it has 3 tensions pulling up on it. A only has 1, so you're going to have the velocity of A plus 3 times the velocity of D equals 0. Now, what was easier? What I just showed you guys there, it's the same equation, or doing it the way the book does it. What do you guys think?
The second way.
Yeah. There's even a third way. Now, this third way, those two methods always work. This third way only works if there's just one movable rope. And in the third way, all you do is you just count the ropes. There's one rope acting on A, so you can put a 1 right there in front of A. There it is, there's the 1. But there's 3 ropes pulling up on, movable ropes that is, pulling up on D. See, this doesn't even have to be a rope, that could be a piece of metal. There's 3 ropes pulling up on D, so you put a 3 there. That's another way of doing it. But that method only works if you have only one movable rope. Now let's do one with 2 ropes, a little more complicated. Well, we're going to do one with, yeah, we'll do a different one here. Okay, here we go. I'm gonna kiss all this goodbye, and we'll do a different one now. Why don't I tell you about relative motion while we got this? There's also something called relative motion. You're familiar with this. For instance, if you're in an airplane and another airplane is coming at you head on, let's suppose, here, I need a little room here to demonstrate this. Suppose you're in an airplane, and here's your airplane, and you're going 150 miles per hour. There you go. And suppose another airplane is coming straight at you, and they're going 200 miles an hour. Well, you're looking out of the cockpit, and you see this other airplane, and when you first see it, it's just a speck. But that speck is starting to get bigger and bigger and bigger. It's time to turn, maybe dive, make a turn, get the heck out of the way, wouldn't you say? Because if he's going 200 straight at you and you're going 150 straight at him, you know what that makes? That makes 350. The relative motion is 350. They call that relative motion. You understand that, don't you? It's a relative motion. The equation for it, let's say this is A and this is B. The equation, the relative motion equation goes like this. Now these really are vectors. And the way you read this is the velocity of A relative to B. Some people say with respect to B. What that means is the observer is at B. We're going to put the observer at B. Here's B. Here you are. I'll draw a little picture. There's the pilot right there. You're in B. Relative motion is relative to the observer. And the velocity of A is 200 miles per hour. And the velocity of B is a negative 150, because see, he's going to the left. That's a negative. Now, if you do the math, you'll get 350, the velocity of A relative to B. Going to the right, because it's plus. This is the relative motion equation. Now, on that problem we just did, if you wanted to do the relative motion equation, let's do that. We just did this thing with the pulleys. Never mind the airplanes for a minute. we're going to find the velocity of A with respect to D, or relative to D. That's what that symbol means right there. That's the velocity of A. It's really a vector. It's the velocity of A relative to D. What that means is the observer is at D. Here, we'll draw a little person here. There, can you see? That's too small. Let's make him a little bigger than that. We're going to draw a little person here. And he lives on D. That's his home there. And he's looking at A. Now he's going up and A is going down. But the velocity of A relative to him is 4 going down. A is really only going down 3, but because he's going up, A appears to be going down 4. I don't know if that made sense, but here's the equation. This is the relative motion equation. Now the velocity of A is 3. Now they decided that going down is plus. Now you could have a plus going up, but it'd be all right, but they wanted it to go down. And now D is going up, so it's there's a minus sign here in the equation, but see it's going up -1, remember? And so what you get when you do the math, you get 4. So the velocity of A relative to this observer is 4 going down. Okay. All right, well, let's do one that's a little more complicated now, if that made sense. Any comments or questions? Okay. All right, well, let's do this one then. Here goes. I'll erase all this. If you just tuned in, the topic for today is we're dealing with pulleys, actually, and dependent motion. We're learning how to write the dependent motion equation. I showed you how the book does it. Let's try this one. This is F1244. Okay, we're going to do F 1244. Yeah. Okay. Well, let me draw it. I think I need more room. Let me give a little bit more room here. It's hard for me to do this, but I'm trying. Yeah. Okay, but now we got something going on here. He comes up here. Maybe that needs to be bigger, I don't know. Yeah. Then what? I'm having all kinds of trouble here. Coming down here, and then we go over this one, yeah. Okay, now that part I did all right. This comes up here, but where does this one go? Guys, let me start all over again. I'm having a heck of a time here. We'll get it. Just be patient. Be patient. Okay, I'm going to draw that one. And then this one comes down. And then it comes down here. Yeah, there we go. And this one, maybe make that a little smaller, not much. Make it a little smaller. Yeah. Yeah, that's better. Yeah. That's not right either. Guys, I'm sorry. I'm having a heck of a bad time here. We're going to get this though. Yeah, here we go. Now it's cooking. Okay. I think I finally got it. Now they label this F and D. All right, that's fine. F and D. And they label that E and C. Okay. It's pretty good. And they label this A and B. Okay. Well, let's do it the hard way the book says to do it. We did get it right, right? Yeah, finally. Okay, we're going to do it the way the book says to do it. And what you need here is you need this distance here. We'll call it y of, how about y of d? That'd be good since that's d. Yeah. That's y of d. And how about this? We could call this y of c. All right, that's y of c. And this here is y of a. Let's do that too. Y of a would be here. All right. Well, I think we're ready to go then. Now we're just going to add up these ropes. Now there's two different ropes. That won't stop us. We're going to take and add up this rope here. See it? And that's going to be well, that's just y of d, isn't it? Y of d. And then we're going to go around this rope or this pulley here. That's going to be plus pi r. And then we're going to go this rope here. That's going to be, now let me think about this. I probably shouldn't have A at the same place there. Let me scoot A up just a little bit so I don't confuse myself. We'll have A go to right here. That's better. What I need, I'm trying to add this piece here. You know what that is? That's y of c. No. It's y of d minus y of c, I believe. Y of d minus y of c. You think? Yeah. Then we're going to go around this pulley here. That's just pi r plus pi r. The r might be different. You can have it R1, R2 if that makes you happy. And then finally, we're going to go this length of rope from here to here. You know what that is? That's y of a minus y of c, isn't it? Yeah. Y of a minus y of c equals, call it L1, the length of the red rope. All right. Now we're going to do the other rope. There's two ropes. Let's color it blue. See, there's a red rope, but there's also this blue rope. So let's color it. Here we go. We're going to go from here to here now. It's blue. Does that show up blue on your thing? Not really. I can't help it. That's what I'm trying to do. I'm trying to add up that rope there. Okay, now that's going to be y of d minus some constant, call it k1 maybe. So you have y of d minus k1 plus, you're going to go around this pulley here. That's going to be a pi r plus pi r. Is that the same r as we had before? No. That's a different R. I don't know, call it R3 or something. We don't care. And then finally, you have this little piece here from here to here. That's y of c minus that k1. Equal, call it L2, the length of the blue rope. I don't think blue really showed up very good on that. Now, if I made a mistake, somebody tell me. Did I do okay so far? Is anybody awake out there?
Looks good.
Oh, gee, let's see who this is. I can't talk right now. Okay, well, let's take the derivative of these. Now, when you take the derivative of that, you'll get, let me do it down here someplace. You get the velocity of d. That'll give you 0 when you take the derivative of a constant, plus the velocity of d minus the velocity of c, plus 0 when you take the derivative, plus the velocity of a minus the velocity of c equals 0. Okay, you could clean that up a little bit. It looks like we have two velocities of d minus a velocity of c. No, there's two of them. Minus two velocities of c plus the velocity of a equals 0. Okay, now that's a keeper. Let me box that up because I'm going to use that here in a minute. But now we're going to look at the second equation. Now, when you take the derivative of this one, you get the velocity of d. That's the derivative of the distance to d. Derivative of distance is velocity minus 0 plus 0 when you take the derivative plus the velocity of c minus 0 equals 0. So that one says velocity of d plus the velocity of c equals 0. Ta-da! There's that one. Now what we're interested in is a and b. We don't care about c. These are the ones that we want to know. So what we're going to do is, for one thing, the velocity of b is equal to the velocity of d. And so we could replace this with a 2 times the velocity of b. And you see the velocity of c is negative the velocity of d. Here, I don't know. This is getting too weird. The velocity of C is a negative velocity of D. So let me do it that way. We got two velocities of D minus 2 times the negative velocity of D. That makes plus the velocity, 2 times the velocity of D, plus the velocity of A equals 0. Now, since the velocity of B and D are the same, you could just add these and you could get 4 velocity of B plus the velocity of A is 0. And we're done. Ta-da! We have just done the, they have a name for that. It's called the dependent motion equation. We just did it. This is problem 1244. But now we could do the same thing with the method I showed you, and it's a lot easier. Put a tension right here for this tension connected to A. You have the same tension around that pulley here, and you have the same tension here. Now, you see these two tensions pulling down on this pulley? That makes this cable or rope or cord 2 tensions. So coming around this side, you have 2 tensions, 2T. Now I want you to look at what you got here. You got a T, a 2T, and a T. That makes 4 tensions. So this strap or pulley or cord connected to B has 4 tensions. You got 4 tensions connected to B, 1 connected to A, and so you can write it like this: 4 VB plus VA equals 0. Wasn't that easier? And now we'll solve the problem. They said here, if you'll read this, A goes down 4 feet per second. All right. If A is going down 4 feet per second, put a 4 right there and solve for B. Well, what you'll get is B is going to go up 1 feet per second. If A is going down 4 feet per second, B will go up 1 feet per second. Now look at the answer, F1244. Let's see if we got that right. Go to the back and look up F1244. They said the velocity of B is negative 1 feet per second, which means 1 feet per second going up. There you have it. Okay, great. Do you have any comments or questions on that? Well, if not, we'll just work some more. But I'm tired of doing it this hard way, aren't you? Let's see if we can do it the easy way from now on. I mean, why go through all that agony? Look at all that mess that we had to do there. It's a lot easier just to do it that way. Okay, well, let's try some more here. Any comments or questions so far? Well, you're awfully quiet. That's all right. Okay, well, here we go. We're gonna try another one now. I'm gonna erase all this if you're happy. All right. Okay, it's Wednesday, September 2nd. We're studying pulleys and how they work. Let's do 12,205. Let's see if I can draw this one without goofing up. Now, did I get this thing drawn? Did I get it drawn right? I think so. Okay. Now let's write the dependent motion equation. Let me be quiet for a minute, and let's let you have a try at it. You write the dependent motion equation, and I'll be quiet, and then we'll see what we think. Go ahead. Okay, time's up. Let's see how we did. Now, we could go back and do it the way the book says, but who wants to? Just put a T right here. Come around here, put a T right there. Come around here, put a T right there. Put a T right there. And a T right there. Now we're going to write our equation. Notice there's one tension on A, so you go 1 VA. Look, there's two tensions on B, so you go 2 VB. Look, there's two tensions pulling up on C, so there's 2 VC equals 0. We have just written, is that what you got? I'm hoping.
Yes, it is.
Yay. Now let's solve the problem. Good. They said A is going down 6 feet per second. All right, let me write that. 6 feet per second. So they decided to call down plus, so that will go with what they said. So you have 1 times 6. And then they say C is moving down at 18. All right. C is moving down at 18. So I can do that. I got 12. Wait a minute. I think it's minus 12. Did I do that right, algebra students, or math? It's really not algebra. It's just addition and multiplication, isn't it? 2 times 18 is 36. It's wrong. It's wrong. 36 and 6 is 42, right? Well, I don't know. Would it be 21? Let me do it on my calculator here.
Yeah, I got 21.
Yeah, well, we should be able to do that. 36 and 6 is 42. And then you divide by 2, you get to, yeah, 21. What does that mean? Well, in minus, if going down is plus, minus is going up. So it means that B is going up 21 feet per second. And C, they said, is going down 18 feet per second. Now let's read the problem. determine the relative velocity of block B with respect to C. Oh, well, we haven't answered their question yet. See, what they want is the relative velocity of B with respect to C. Now, here's how the equation goes. That's how you do the equation. Now, what is the velocity of B? Well, it's minus 21, right? And there's a minus sign in the equation. What's the velocity of C? It's a plus 18, isn't it? They said going down is plus. So I'm getting 39, right? Yeah. I'm getting this here is minus 39. What does that mean? Well, that means if you live on C, here, let's put our little observer right here. Here's our little observer. See, I drew a little man right there, a little woman there, whatever. The person is riding along there, and they're going down, and they're looking at B. Well, B is going up, and they're going down. To them, B seems to be going up 39. They think B is going up 39 feet per second. Now let's look at the answer. 12,205, go to the back, and we'll see how we did. 12,205. They said 39 feet per second going up. The answer is 39 feet per second going up. So we did great. We did that. Okay, let's do some more. Let's do this one. Any questions on that, though? All right. Well, let's do another one if you're happy. I'm going to erase this. There's your chance to ask a question. Okay. Now this one is 12,199. They've got a, it looks like a log there maybe. Yeah. They've got some kind of log here. And they put a pulley on there. And they've attached this pulley. Well, it's actually attached to a tree, but we'll just draw something solid there that it's attached to. They're going to call this C here and call this B. And this log is on the ground, and they got this connected to a pickup truck, looks like. And the truck's is going to pull that. First, we're going to get the dependent motion equation, and then we're going to write their equation. Then we're going to answer their question. Okay, now this is a pickup truck here, actually. There you go. What we need is the, I think we're going to call this log B. What we're going to do is we're going to find the dependent motion equation. And I'm going to be quiet. And what I need is I need you to relate the velocity of the pickup truck, which is C, to the log, which is B. Okay, I'm going to be quiet for 1 minute, and I want to see if you can write the dependent motion equation. Go for it. Okay, your minute is up. If you put a tension here on this cable, you'd have a tension on that cable and a tension on this cable. And if you look at this body B, it's got 3 tensions on it. And so you would have 3 velocity of B and here's where we're going to run into a problem. You have to decide see, I think this is going to have to be a minus. I know it's going to be 1 velocity of C. It's going to look like this, but is it plus or minus? Well, the thing is, we know B is going to, they're both going this way, right? Obviously, they're both going that way. We're going to define this as the positive direction. And so you've got to have a minus here. You understand about the 3 and the 1 business, because that's got 3 tensions pulling on it, and there's only 1 tension on the pickup truck. But why the minus? Well, because if this is positive, that can't be positive. You can't add a positive and get 0. So now I'm not doing a very good job of this, I know. We know that I think the equation's got to be like that. There's 3 there and 1 there. But why does it have to be minus? Well, because if this motion is positive, and if this motion is positive going this way, you have a positive minus a positive. You can get 0 with that, yeah. Kind of makes sense. Okay, let's answer their question. Now, what did they say? They said find the displacement of the log if the truck pulls the cable 4 feet to the right. This truck goes 4 feet. Well, now these are velocities. To get distances, you would have to integrate. The way it works is the integral of v dt is equal to your distance. Here, let me refresh your memory. Velocity is equal to the derivative of distance with respect to time. See if you can get to here with me. I know you can go from there to there. And then when you integrate, this will give you your displacement or the change in your position. And so when you integrate this, you'll get this equation here. Is there room to write this? Barely. You get 3 delta S of B minus 1 delta S of C equals 0. Now they said that C goes 4 feet. So you put a 4 there. Goes to the right. We just said that's positive. So you have 3 times something minus 1 times 4 is 0. Well, that must mean that the distance that B goes, probably should have put an X there. You know what? Instead of S, we could have just put an A. That S is just a dummy variable. But the distance that B goes is 1.333 feet. Because 3 times 1.333 will give you 4. Subtract 1 times 4 gives you 0. The tree goes 1.333 feet. The pickup truck goes 4 feet. But that goes 1.3, 1 1/3 foot. All right, great. Look in the back. Let's see how we did. 12,199. 12,199 says 1.33 feet to the right. We got that right. Yay. We did good. Any questions so far? Okay. Well,
Yeah, I had a question about the tension method. Could you start at the log at B and work out the t's going the other direction, or is it important that you started at point C and work the t's out going that direction?
you could start at B and put it. Now, who am I talking to?
This is Taylor.
Taylor. Okay, now, Taylor, if you did it that way, here's what you'd have to do. You'd have to call this T right here, wouldn't you, Taylor?
Right.
And so this would be a T over 3, and this would be a T over 3, and this would be a T over 3. And so this one here would be a T over 3. And what you'd have is 1 velocity of B plus 1/3 the velocity of C equals 0. Now, you can do some algebra, and you should be able to multiply by 3 on everywhere. And you should get this here, which is what we got. Yay, that's what we got. Did that make sense?
Yes, it did. Thank you very much.
Yeah, anytime. So it's easier to start with the thing that has just one rope connected to it and call it T.
That is easier.
Yeah, it's a little easier. Okay, now I mentioned you can get displacements from this. You can also get accelerations. Here's a little room right here. Let me write that for you. If this is the equation for the velocities, this is the equation for the accelerations. because it's just the derivative. If you take the derivative of this, it's 3 times the acceleration. There's a minus sign. If you take the derivative of this, it's the acceleration. Of course, the derivative of that 0 is just 0. So you can get displacements and accelerations and velocities. These are all dependent motion equations. Okay, well, we got 9 minutes. I wanted to show you one last thing. On the relative motion equation, this one here that we told you about, we've just been working in one dimension. Let's show you how that if you deal with vectors in 2 or 3 dimensions, it's still good. That equation is still good. It's just that we're dealing in 2 dimensions now. Now let's do one. Here's one that looks like fun. This is problem 12, 218. Now I wonder if they have, let me see if they have answers in the back, because I want to see if we can get it. 12, 218, do they have answers in the back? Yes, they do. I'm not going to peek. Okay, now here's the deal. Here's this airplane here. Yeah, going straight down. Not a very good picture, but we tried. There's this airplane. And it's going 500 kilometers per hour. Okay, straight down. That's the velocity of airplane A. Now here we've got the velocity of airplane B doing this. Velocity of airplane B, this is no longer just one-dimensional. It's 700 kilometers per hour. And this angle here, there's an angle here. Boy, I didn't do that angle very good. It's supposed to be 60 degrees. Let me try doing it better. 60 degrees would be more like that. Here's your airplane here. And this is 60 degrees. And this one's 700 kilometers per hour. It's going this way. So there's your velocity of B. And the velocity of A is 500 kilometers per hour. It's going this way. Okay. Well, here's your equation. Now, what do they want to know on this? Let me read this. Determine the velocity of B with respect to A. Well, that's what this is. We're going to solve this equation. We're going to find the velocity of B with respect to A. Do you know where the observer is? Where's the observer in this relative motion equation? Let me pick on one of my wonderful students here. Jackson, which one is the observer in this equation? Unmute, Jackson. Tell me which one's the observer. You have a 50-50 chance of getting this right.
Would it be A? Or
Yeah, you got it right. Good going, Jackson. You might have good luck at the casino after all. Just kidding, Jackson. The A is the observer. Here, let's put well, there's a little pilot. There's a pilot. He's looking at this plane here, and we're going to write the relative motion of B relative to him. Now, how do you do that? Well, you have to subtract vectors. I don't know if you remember how to do that. The way they taught me in school to subtract vectors many years ago, you put their tails together. I wonder if they still teach that. You put their tails together. So here, let me do that. You really need a protractor to do this right. So what I'm going to do is I'm going to make a I'm going to make a 700 kilometers per hour. Let me do the 500 first. Okay, here's the 500. I'm doing this to scale, actually. I did 5 inches there. There's your 500 kilometers per hour. And that's your vector. But now we're supposed to put the tails together. Well, how do you put the tail on that? Well, that's the tail. I need a 700, but I need it to go up from here. What angle will that be? Well, let's see. Now, if that's 6, that means that's 30, huh? I need a 30-degree angle. How do I do that? Or would it be a 60 from here? Let's see. I think it's 60 from there. Okay, now there's 60. Oops. And I need 700. I need some room here. I'm not real sure I did that right, but we'll double check it. Okay. This is how you subtract vectors. See, what I'm trying to do is I'm trying to subtract the velocity of A from the velocity of B. And the way they taught me in school, here's the velocity of A. It's 500. I measured it. 5 inches. Oh, gee, I'm running out of time. And then this one here, I made this angle. Wait a minute. I think I did that wrong. I need a 60-degree angle up there. I don't think I have that. Oh, gee. I need a 60-degree angle up there. Yeah, I do. There's 60. Yeah, I did pretty good. So that means this would be 30 down here. Yeah, it is. I did that right. And so this one is 700 kilometers per hour. There we go. And where does the vector difference go? Well, it goes from A to B. It goes all the way up to here like this. Did they teach you this in school? That's it. And I tell you what that is in inches. It's about 11. So the velocity of B relative to A is around 1,100 kilometers per hour. But see, it's at an angle going up. And that angle going up is, I could get this exact with the more time, but we'll look and see how we did. This turns out to be dang close to 60. It's more like about 50. 58 maybe. It's hard for me. I need my glasses on, I guess. It's around 57, 58. We're talking about this angle here. It's around 57 degrees. Now let's look at the answer because we're running out of time. It's sad. But look in the back at 12, 218, and let's see what they said the answer is. 12, 218. There it is. Now they said it's, here's what they said the answer is. It's 1044 kilometers per hour at 54.5 degrees. Now, we're off because of my graphical method. I said 57 degrees, they said 54.5, so I'm a little off. I said 1100 with my crude 11-inch ruler there, and they said 1044. To get it correct, oh, we're out of time. To get it correct, you'll need to convert these into X and Y, and subtract them, and you can get the exact amounts, and you'll get the right answer. But this is what it looks like. If you live in this airplane here and you're flying along, this airplane appears to be coming kind of at you, but he's also kind of moving this way. He's coming at you, but he's moving to from your right to your left. Oh, it's sad, but we're out of time. Okay, well, enjoy your homework, and I will see you. Now, wait a minute. Is Monday a holiday? We better look and see here.
I think it is.
Yeah, it's Labor Day.
Let's look and see here. This is yeah, there is no class on the 7th. It's a holiday. It's Labor Day. But you do have homework. You can do your homework and you'll be happy. But I won't see you till a week from today, right? Yeah. Yeah, because Monday's a holiday, Labor Day. All right, well, here's your last chance to say anything. I'm going to sign off. Any comments or questions?
Have a good week.
Have a good week. Be careful. Thank you for showing up, everybody. See you next time, a week from today, right? Bye-bye.